Welcome to our Bioprocess Engineering online tutorial on Bioprocesses economic evaluation. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. In this introductory tutorial on the economic evaluation of bioprocesses, we'll address three questions: how to evaluate investment costs, how to evaluate production costs, how to analyze bioprocesses production costs. Additionally, we will examine two examples of bioprocess costs. Bioprocess cost is a critical performance criterion for enzymatic bioconversion, microbial fermentation, and animal cell culture processes. Addressing cost issues is essential when designing the sequence of unit operations that transform raw materials into products, selecting the appropriate equipment for these operations, optimizing the process operation to ensure efficiency and cost effectiveness. When assessing the economics of bioprocesses, two types of costs are evaluated: the capital investment cost, also called CapEx, capital expenditure. This cost, measured in dollars or euros, represents the initial capital required to acquire the equipment, install it, and make it operational. The production cost, also called OPEX, the operational expenditure. This cost, measured in dollars per year or dollars per kilogram of product, encompasses the ongoing operational expenditure for producing the product. The capital investment cost includes all expenditures required to establish the bioprocessing facility. To evaluate this cost, the initial step involves selecting industrial equipment for the unit operations that compose the process. Commonly used equipment in enzymatic, microbial, or animal cell bioprocesses includes tanks, bioreactors, fermenters, heat exchangers, centrifuges, evaporators, ultrafilters, microfilters, chromatography columns, and dryers. The second step involves sizing the equipment. Equipment sizes are determined based on the quantities of processed material and the desired purity level of the product. Specific expressions for equipment sizes include volumes for tanks and fermenters, surface areas for heat exchangers and ultrafilters, hourly capacities for centrifuges and dryers. The third step involves evaluating the purchased equipment cost, PEC. The cost of equipment is most accurately obtained directly from equipment providers. Alternatively, it can be approximated using available graphs that depict the equipment purchase cost as a function of its size. These graphs often show a relationship close to a straight line when plotted on a logarithmic scale, or sometimes two segments of straight lines. Consequently, the PEC purchase cost can be approximated as a function of size using the equation PEC equals A, size to the power NNN, where A is the cost of equipment for a unit size and N is a scale coefficient, which is less than 1. The fourth step involves evaluating the initial capital investment. This is calculated by adding to the purchased equipment cost additional expenses for equipment installation and operational setup. Capital investment encompasses costs for piping, instrumentation, electrical systems, buildings, land, engineering, and construction. It also includes expenses for equipment testing to validate the industrial plant. Capital investment is typically determined by multiplying the purchased equipment cost by a multiplier MCI over PEC. This multiplier generally falls within the range of 4 to 6 for the production of chemical or biochemical products. However, for biopharmaceuticals, it is significantly higher, typically ranging from 8 to 12. Capital investment costs for bioprocesses can reach tens to hundreds of millions of dollars. The bioprocess production cost is initially evaluated per batch or annually, and subsequently per kilogram of product. It encompasses all expenses related to materials, energy, equipment usage, and labor. The materials cost is determined based on the consumption of materials during process unit operations. Examples of raw materials considered include sugar and ammonia, used as carbon and nitrogen sources in fermentation media, as well as water. To calculate the cost of materials, the consumption of each material in kilograms is multiplied by its unit cost in dollars per kilogram. The energy cost is determined by assessing equipment energy consumption in the form of electricity, gas, or fuel. Electricity is consumed across all unit operations, particularly for tank agitation and fluid pumping. Gas and fuel consumption provide heat essential for thermal operations, such as sterilization, evaporation, and drying. The cost of energy is calculated by multiplying the consumption of electricity in kilowatt hours, of gas in cubic meters, or fuel in liters by their unit costs. The equipment cost encompasses three components: equipment depreciation cost, operating cost, and equipment consumables cost. The annual equipment depreciation cost is computed by dividing the capital investment by the number of depreciation years, typically around 10 years. The annual equipment operating cost includes expenses for equipment maintenance, insurance, and other taxes. This cost typically ranges between 6% and 8% of the capital investment. Additional expenditures for equipment consumables include costs for resins used in chromatography columns, as well as membranes for ultrafilters or microfilters. The labor cost comprises three components: the salary cost of technicians, the salary cost of supervisors or engineers, and the overhead costs of the company. The technician cost is calculated by multiplying the required hours of technicians by their hourly salary. Supervision hours are typically estimated to be between 10 and 20% of the technician hours. The supervision cost is determined by multiplying these hours by the hourly salary. Overhead costs of the company include expenses related to administration, management, buildings, and offices. These costs generally amount to approximately 50 to 80% of the total salary costs of technicians and supervision. Production costs for bioprocesses can vary significantly, ranging from less than $1 to millions of dollars per kilogram of product, depending on the nature and purity of the product. Bioproducts in the range of $1 to $10 per kilogram include high-volume products such as ethanol, organic acids, amino acids, polysaccharides, and fermented foods and beverages. Specialty chemicals and drugs like antibiotics typically have production costs ranging from tens to hundreds of dollars per kilogram. The highest production costs are associated with therapeutic proteins and vaccines, which can range from hundreds of thousands to millions of dollars per kilogram. For the design and optimization of bioprocesses, it is valuable to supplement the production cost evaluation with an analysis of cost contributions. This includes assessing the cost percentages allocated to materials, energy consumption, equipment usage, and labor expenses. It is also pertinent to determine the relative significance of the upstream operations, encompassing media preparation and biotransformation, compared to the downstream operations, which involve separation and purification. For biopharmaceuticals, where product purity is critical, the downstream processes typically contribute significantly higher to overall costs. Bioprocess cost evaluation should be complemented by an assessment of its uncertainty or precision. Uncertainty typically represents the 95% confidence interval of the obtained cost, calculated using statistical methods such as uncertainty propagation. During the stages of bioprocess development, uncertainty tends to decrease progressively. For instance, it may start at around 50% and reduce to 10% or less by the project's completion. As a first example of bioprocess cost evaluation, let's consider the production of a large tonnage amino acid, glutamic acid, obtained by microbial fermentation. In the upstream section of the process, the unit operations include the preparation of the fermentation media, the media sterilization, and the fermentation. Meanwhile, the downstream section involves centrifugation, evaporation, crystallization, and the final step of glutamate crystals drying. A glutamic acid production plant, equipped with a 200 cubic meter fermenter, is designed to produce 4,500 tons of glutamate annually. The sizing of other upstream and downstream equipment determines the volumes of the media preparation tank and crystallizer, the surface area of the heat sterilizer, evaporator, and rotary dryer, and the capacity of the centrifuge. The capital investment for the plant is approximately $18 million. For this glutamic acid production plant, the annual production cost is $13 million, equivalent to approximately $3 per kilogram of glutamate. Analysis of the production costs reveals that nearly 50% of the total cost is attributed to raw materials, primarily fermentation sugars. Equipment usage accounts for approximately 20%, while labor and energy contribute about 17% each. The second example of bioprocess cost evaluation involves the production of therapeutic monoclonal antibodies using animal cell culture. The upstream section of the process includes unit operations of media preparation, media sterilization through filtration, and cell culture. In the downstream section, operations involve centrifugation, filtration, chromatographic purifications, viral inactivation through filtration, and diafiltration. A monoclonal antibody production plant featuring a 10 cubic meter bioreactor is designed to produce 300 kilograms of antibodies annually. The sizing of other upstream and downstream equipment determines the volumes of the media preparation tank and chromatography columns, the surface area of the filters and ultrafilters, and the capacity of the centrifuge. The capital investment for the plant is approximately $80 million. For this antibodies production plant, the annual production cost is around $27 million, equivalent to approximately $90,000 per kilogram of antibodies. Analysis of the production cost indicates that 56% of the total cost is attributed to equipment utilization. Culture media account for approximately 15%, labor 19%, and consumables about 11%. Energy cost is negligible. In conclusion, in this introductory tutorial on bioprocess cost evaluation, you learned the methodology for assessing the capital investment required for bioprocess plants, based on equipment sizes. The methodology for evaluating bioprocess production costs, considering expenses related to materials, energy, equipment usage, and labor. As highlighted, production costs can vary significantly depending on the nature and purity of the product. If interested, you can gain a deeper insight in Bioprocesses cost evaluation by enrolling to one of our 2 online courses, Introduction to Bioprocess Design, Scale-Up and Simulation, and Design and Cost Evaluation of Bioprocesses. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.